Artificial intelligence includes machine learning, which allows systems to learn from experience and get better without having to be explicitly designed. It involves algorithms that examine data, spot trends, and use that information to forecast or decide what to do. Different kinds of machine learning exist. Supervised education. Supervised education, the algorithm is trained on a labeled dataset in supervised learning, where each input has a corresponding target output. From the given labels, the algorithm learns how to map inputs to outputs. Neural networks, decision trees, support vector machines, logistic regression, and linear regressions are examples of common algorithms. Unsupervised learning. Using unlabeled data, unsupervised learning entails training algorithms with the goal of identifying patterns, structures, or correlations in the data. Common tasks in unsupervised learning are dimensionality reduction and clustering. Principal component analysis, autoencoders, k-means clustering, and hierarchical clustering are a few examples of algorithms. Semi-supervised learning. This type of instruction blends aspects of both unsupervised and supervised learning. To enhance learning, it makes use of a smaller quantity of labeled data in conjunction with a larger quantity of unlabeled data. This class of algorithms includes label propagation, co-training, and self-training algorithms. Reinforcement learning. In order to maximize cumulative rewards, agents are trained to make sequential decisions in an environment. Through trial and error, the agent gains knowledge and receives feedback in the form of incentives or sanctions, depending on its performance. Q-learning, policy gradients, deep Q networks, and active critic techniques are examples of common algorithms. Self-supervised learning. This sort of unsupervised learning involves the model creating labels on its own based on the input data. Pretext tasks are commonly employed in this methodology, wherein the model is trained to anticipate specific attributes or modification of the input data. Enhancement of performance on downstream supervised activities can frequently result from pre-training on self-supervised tasks. Online learning. In online learning, the model continuously updates its parameters by learning from newly available data examples. This method works effectively in situations where data must be instantly adjusted to changing circumstances and streams in real time. Transfer learning. This refers to the process of using information from one activity to enhance performance in a related but unrelated task. Pre-trained models are refined on fresh datasets or tasks rather than being trained from scratch, which saves time and computational resources. Meta-learning. Models that can learn how to gain insight are the main goal of meta-learning, commonly referred to as learning to learn. In order to enable them to swiftly adapt to new tasks with minimal training data, these models seek to gain information or methods from multiple tasks or domains. One-shot learning. In one-shot learning, a model is taught to identify or categorize objects using just one sample from each class. This method works especially well when working with new classes or when there is a lack of labeled data. Analogical learning. Analogical learning is the process of learning by comparison in which a model finds commonalities or connections across various instances or fields. Because of this method, which draws inspiration from human reasoning and cognition, the model can generalize knowledge across different contexts. Ensemble learning. Ensemble learning combines multiple models to improve performance, often by averaging predictions or combining them through voting mechanisms. Techniques include bagging, boosting, and stacking. Active learning. Active learning involves iteratively selecting the most informative data points for labeling to train the model more efficiently, reducing the need for extensive labeled datasets. Bayesian learning. Bayesian learning models uncertainty and updates ideas about parameters based on observed evidence, resulting in more reliable predictions and decision making. It does this by incorporating probabilistic reasoning. Gaussian processes. Regression and classification are made flexible and comprehensible by Gaussian processes, which are probabilistic models that describe distributions or functions. Deep reinforcement learning. This technique addresses difficult sequential decision-making issues, frequently in settings with high-dimensional input spaces, by fusing deep learning and reinforcement learning. Evolutionary algorithms. These are especially helpful for issues with non-differentiable objectives or complex search spaces, as they emulate the process of natural selection to optimize solutions through iterative generations. Imitation learning. Also referred to as learning from demonstrations, imitation learning teaches models to imitate expert behavior by the observation of trajectories or demonstrations, hence facilitating learning from human expertise. Multi-instance learning. This technique allows the model to learn from sets of instances rather than single samples, It works with datasets where each example is a bag holding multiple instances. Differential privacy. By introducing noise to training data or query responses, differential privacy seeks to offer robust privacy assurances by making sure that specific data points cannot be deduced from the output. Sparse coding. This technique, which is helpful for tasks like feature extraction, denoising, and compression, learns a compact and sparse representation of data. Manifold learning. Manifold learning approaches seek to reveal the low-dimensional structure that lies behind high-dimensional data in order to facilitate data distribution comprehension, dimensionality reduction, and visualization. Markov decision processes. The theoretical basis of reinforcement learning, Markov decision processes simulate decision-making in stochastic contexts with sequential actions and states. Neuroevolution. This method allows neural network construction and optimization to be done automatically by using evolutionary algorithms to evolve neural network structures or parameters. Multi-label learning. This technique uses datasets in which an example can be in more than one class at once, necessitating the use of specific algorithms to manage the label dependencies and correlations. Semi-supervised clustering. By utilizing the knowledge present in both forms of data, semi-supervised clustering enhances clustering performance by combining labeled and unlabeled data. Online-Convex Optimization. To optimize performance under dynamic situations, online-convex optimization techniques actively modify model parameters in response to incoming input. Quantum machine learning. In order to improve machine learning algorithms and maybe achieve exponential speedups for some tasks, quantum machine learning investigates an application of quantum computing principles. Causal inference. To help decision makers discern between correlation and causation, causal inference techniques attempt to infer causal links from observational data. Self-organizing maps. Self-organizing maps are methods for unsupervised learning that preserve topological links between data points while organizing high-dimensional data into low-dimensional representations. Temporal-Difference learning. This reinforcement learning method allows for effective learning in sequential decision-making tasks by updating value estimates depending on the variation between subsequent predictions.